Okay, so I want to do another example or two of graphing inequalities. And I'm purposely going for my next one to be example 3 out of your notes. So that's why I've pulled up number 3 in this particular video, because I like that it's already factored and everything's on one side of our equal sign. So a couple of things I'm thinking about in terms of what I'm viewing. I noticed there are 3 zeros, right? One at 0, one at 5, and one at 4. And so initially I might go to my number line if I'm going to draw a sign chart and plot those points, right? There's a 0, there's a 5, and then there's a 4. And I might distinguish this one because it's greater than or equal to. I might actually distinguish this one with a solid dot to indicate that those are, in fact, like solutions, right? So it's going to be closed bracketed for those endpoints because I can actually equal those values. Okay. Then realizing now there are 3 points, there are 4 regions. So there's the region that's bigger than 5, right? There's the region that's in between 4 and 5. Oh, that's what I get for doing a video in the passing period. There'll be another bell in 2 minutes. And then between 0 and 4, and between or less than 0. So there's 4 regions. So the idea of a sign chart is to pick a test point, but we can be efficient in our picking it of test points. Like, if we pick, let's say x equals 6, if we pick a test point here, but we recognize the behavior in the multiplicity of all of our exponents, we only have to pick one test point. And I'll explain that. So x equals 6, if I put 6 into all of those factors, I don't really necessarily care what the value is. And again, you don't have to necessarily write this out. This is just you seeing into my brain, right? That's kind of awkward. But I know that when I put 6 into this function, because 6 is bigger than all the things that I'm subtracting, I know this is going to be positive. In other words, I know it's a positive number. I don't really care necessarily what the number is. I just care that it's positive. So I know that region gives me positive values. I picked one element as a test element. Everything in that region will be positive. So I'm claiming now I don't have to test any other points because I can look at the behavior of 5. The behavior of 5, go back to highlighter, the behavior at 5 in terms of this factor, the behavior of 5 has a multiplicity of 3. It's an odd multiplicity. So thinking back to graphs that changes signs, it crosses the x-axis, goes from positive to negative. The same is going to happen here, right? So if on one side of 5 is positive, like on the right side is positive, then the other side of 5 has to be negative. You have to switch signs at that 0 based on this behavior. See? I said 2 minutes to the mark, right? Now, look at the behavior at 4. The behavior at 4 is determined by this exponent, which is even. So that means that we have to mirror the image. It has to bounce, right? We're not crossing through. So if one side is negative, its mirror image would also be negative. So we could build from that without actually having to test a point. We don't necessarily have to test a point here to show that that's going to be negative. We could base it on multiplicity. And then at 0, it's determined by a coefficient or a exponent of 1, odd number, which means we cross. So if one side is negative, the other side would be positive. So again, based on multiplicity, the behavior at these zeros would follow just like we were graphing polynomials. Like, is it stay positive or is it cross positive negative? Like crossing the x-axis or bouncing. That behavior is determined by, is it even or is it odd? And so again, we're looking for things, going back to your problem, we're looking for things that are greater than or equal to 0. So where are the positives? So we will give this as interval notation, going from negative infinity up to 0, close bracket. And then union, where else is a positive? Close bracket, 5 to infinity. And then we're almost done. This is one of those really weird answers because there's one more point that works, right? Because remember the theme was greater than or equal to 0, right? There's one point that's equal to 0 that's not part of my interval, and that point is 4. So I have to somehow say also 4, union the point 4. So now I've seen quite a bit a variety of how do you express a point as an interval. What I just did is fine, but really if you wanted to be really specific, you should say closed interval 4, comma, closed interval 4. I guess that's more more correct, I guess. But it's a weird answer because you need 1 point. And that 1 point numerically actually fits in between these two intervals. So, if you might want to really say, oh, that's negative infinity, comma, 0, close bracket, union, 4, comma, 4, close bracket, union, close bracket, 5 to infinity. Okay. Now, the other lens you could have seen this is through graphing. Overall, if I look at what's the power function here, so the overall power function is 1, 2, 3, 4, 5, 6. So it's a positive even. And so overall, if I were to have graphed this power function, that starts here, ends here, I know that I've got a 0 at 0. I've got a 0 at 4, a 0 at 5, and then looking at the behavior at 0, you cross through. You look at the behavior at 4, it bounces, so you're down like this, and the behavior at 5, it crosses like a little squiggle. And then, where is it positive? So again, anything that's above the x-axis, which is up here, we know that's positive. So we know that would be our solutions. And then that's exactly what we found, right? That are less than 0, right here, less than or equal to 0, greater than or equal to 5, and the 1 point at 4. So, okay. So again, 3 different ways to think about how do you graph this. But I think you choose any one of those 3. And I hope that makes sense. I hope you're able to see that that process. So, okay, you know what? Let's go. I'm just so excited. Let's just do one more example. Let's bounce up to number 2. Why not? I'll be able to sleep tonight. You'll be able to sleep tonight. So the thing here is that you want to make sure that it's equal to 0. So I'm going to subtract this over. I'm going to say x to the 4th minus 9x squared is less than 0. Do not divide by x squared because you will lose some solutions. Okay, so then I'm going to factor out this x squared, and I notice it's x squared minus 9 is less than 0. Going on with the alliteration theme, I can factor further, x squared, x minus 3, and x plus 3. I want that less than 0. So again, if I do the sign chart, I have a 0 at 0. I'm gonna make that open because I know it's strictly less than that value. So there's 0. Here's 3, and here's negative 3. Okay, thinking multiplicity. This has a exponent of 1, exponent of 1, exponent of 2. So remember, when it's odd multiplicity, it is an intersect. When it's even multiplicity, it bounces. So I know that I'm going to take one test representative. I'm going to pick something over here. I'm going to pick 4. I'm going to pick x equals 4 and test it. And when you put 4, I'll change colors so you can see what I'm thinking. When you put 4 into all of these factors, I don't really care what the output is. I care what's the parity. Is it positive or is it negative? It's positive. Right? You put 4 into this and you multiply all those positive numbers, you get a positive value. So right away, I know every value in this region will be positive, and that because I picked one representative. Now, I'm either going to, I look at the transition at 3 here, it's either positive or negative, but look at the multiplicity. Where did that factor come from? It came from a factor that has odd multiplicity, which means that you have to change signs, positive to negative or negative to positive. And then, so it's at 0, its multiplicity is even, which means it's a touch and go. The behavior is mirrored. So if one side is negative, the other side is negative. And then I'm working my way across to -3. That came from, again, an odd parity there, right? So it's an odd multiplicity. So if one side's negative, the other side is positive. Okay. Now, it might take some getting used to this even odd property in terms of crossing or bouncing, but I think it becomes efficient in the end. And if that doesn't work for you, you could always do test candidates and test each region. I strictly want things that are less than 0. So when things that are less than 0 would be this region here and this region here. So my final answer would be -3 to 0, open-ended, union 0 to 3. Open-ended because it's strictly less than 0. And it's initially it might be awkward because 0 is a boundary here, but you cannot include that. You may also write it like this: -3 up to 3, leave them both open-ended. Then you could say, but x can't equal 0. So that's another way to throw out just a singleton point. So, okay. So there, I promise that's it. I won't do another example in the video, even though I want to just keep doing math. Look through this again if you have any questions, and then we will continue inequalities in class tomorrow. So very nice job. And like I said, keep up the great work.